I hope by now you've gotten comfortable with adding and subtracting integers. Now it's time to round out our arithmetic instructions by multiplying integers. Let's look into how assembly language handles that multiplication. To get us ready for that, though, let's look at the concept of combining registers to make a larger storage space. If we split the AX register into its two halves, we get the AH register and the AL register. Now those can be treated separately. You already know that. Look at the AL register though. Its least significant bit is the ones column, to its left is the twos column, to its left is the fours column, and so on. The most significant bit in the AL register has a value of 128. That shouldn't be news to anybody. But if I let the AH register act as a continuation of the AL register, then the least significant bit of the AH register actually becomes the 256th place. In other words, 2 times the highest bit in the AL register. So when you combine them, if all of the bits are ones, you could store an unsigned number as large as 65,536. And when you think about it, that's all the AX register really is. It's the combination of those two registers that could be treated separately or together. Hold on to that thought for a little while. Let's do something similar with the AX and the DX registers. If you look at the AX register by itself, its bit values go from 1 all the way up to 32,768. That should be an 8 right there. But if we chose to combine the AX and the DX registers, then the least significant bit of the DX register would be 2 times the most significant bit of the AX register. And that's where we're getting the 65,536. Notice the most significant bit then in this arrangement, if there's a 1 in that column, stands for over 2 billion just by itself. So if I put these two registers together, I could store a number that's bigger than 4 billion. And finally, if I combine the EAX register, which is 32 bits, with the EDX register, which is also 32 bits, I'd have 64 bits of storage space. Notice at the far right end, the least significant bit of the EAX register is the ones column. And the far left bit of the EDX register stands for this huge number right here. And if all the bits in these two combined registers were ones, then I could have a value as large as this. So keep in mind, this idea of combining different registers for a larger storage space is fundamental to multiplying in assembly language. Here's the multiply instruction for unsigned integers. I can multiply 2 8-bit things, or I can multiply 2 16-bit things, or I can multiply 2 32-bit things. What's weird about this instruction is that it appears to have only one operand. Actually, it has one explicit operand, and the other one is an implied operand. Here are the explicit operands, and these are the implicit operands. For example, if I say multiply BL, that really means multiply whatever is in this 8-bit BL register times what's already in the 8-bit AL register. And if I say multiply CX, that really means multiply what's in the 16-bit CX register times what's already in the 16-bit AX register. And finally, if I say multiply N1, where N1 is a 32-bit variable, that really means multiply that variable times what's already in the EAX register. Okay, so if I'm multiplying 8-bit values, I first have to put one of the values in the AL register and the other value in either another 8-bit register or an 8-bit memory location. An example would help. Let's say I want to multiply N1 by 10. Now I can do that as 8-bit multiplication. So I put the 10 into AL, and then I use the multiply instruction like this. But here's the deal. The result is stored into a space formed by combining the AH and AL registers, as we saw before. If you think about it, That makes sense because the largest value you could get when multiplying two 8-bit values is 16 bits. Just to make sure we've got this, the result of the multiply is not in the AL register, but rather in AH combined with AL. Let's take a look at Visual Studio. Look what the AL register currently has in it, 0. When I load 10 into it, you can see just the AL register change. The rest of the EAX register is left alone. Then notice what the AH register has, F9. So then we multiply, and now AL has FO hex in it, and AH has 0. Why? It's because FO is 240 in decimal, which can totally be contained in the 8-bit AL register. So AH is 0 because none of its bits were needed to store the result. Now look at the carry flag. It's cleared, meaning there is no necessary data in AH. So the AX is stored into the result1 variable. We can make memory 1 look more presentable like this. Yeah, now it's in decimal. Unlike add and subtract, the multiply instruction is ripe for errors. Take a look at this. Notice the original values in AL and AH. Then I store 10 into AL. So far, just like we did before. Then I multiply by N2, which is a 16-bit value. You'd expect the assembler to complain about something, what with AL being 8 bits and N2 being 16 bits, but no, it doesn't say anything. Now look at AH and AL, and the carry flag. It's set. AH and AL contain 6D30 hex, which in decimal is 27,952. Wait, what? 10 times 3,000 is pretty much 30,000. What happened? The mistake is in thinking that we're multiplying 10 times 3,000. The assembler chooses between 8-bit, 16-bit, and 32-bit multiplication based on one thing, the explicit operand, which means we really just did a 16-bit multiply, not an 18-bit one. And that means the result is stored in the DX and AX combination of registers like this. Oh man, when I look at DX, it's got OB66 hex, and AX has 6D30 hex, which combine to equal, well, let's see, 191,262,000. Not what we expected. Here's a better way. First of all, since we declared the result variable as a word, let's just assume the result of a true 8-bit multiply will always take up 16 bits and use the AX register to store the answer, like this. We're multiplying 100 times 24. Both of those are defined as 8-bit values. I get the answer, 0960 hex, in the AH and AL combo. Look at the carry flag. It's set, which confirms I need both the AL and the AH registers to hold the result. When I store AX into the result variable, I get the expected 2400. Now let's take a look at 16-bit unsigned multiplication. I've commented out these lines just to illustrate what can happen if you don't have these in your program. We'll put them back in here in just a minute. I'm multiplying 750 times 400. I know I'm in at least 16-bit territory now because these numbers are too large for a byte. Let me step through the code. I put my values into AX and BX this time. I want you to see the explicit operand can be a register as well as a memory location. What it can't be is an immediate value, like 20. Now we get to the multiply instruction on line 23. Before it executes, notice what's in the EAX register and what's in the EDX register. Now, after the multiply instruction, the AX register contains 86A0 hex. But notice the top half of that register still contains what it did before the multiply instruction. Then look at the EDX register. The DX half contains 1, but the top half still contains what it did too, before the multiply. Since we did 16-bit multiplication, the result has its low-order bits in the AX register and its high-order bits in the DX register. It's just like in this figure that we've seen before. That means the 1 in the DX register should really be just to the left of the 8 in the EAX register. One way to get it there would be to shift the 1 in DX 16 bits to the left, then add it to the EAX register. Yeah, that's what I should do, but notice those two lines of code are commented out on lines 24 and 25. So watch what gets stored in the result 2 double word. We get a value of over 3 million. Let's try this again. Same setup as before, but this time I clear out the EAX and the EDX registers before I start. Not a bad habit to get into. So I'll step through the code and move my values into the BX and the AX registers like I did before, which will bring us to line 23. After the multiply instruction on line 23 executes, the AX register once again contains 86A0 hex, but the top half of the EAX register is clear because of line 19. The DX register contains 1, but the top half of the EDX register is clear also because of line 20. So now when I execute line 24, watch the 1 in the DX register shift 2 bytes, that is 16 bits, to the left. And then line 25 adds the entire EDX register to the EAX register, which means EAX now contains our result as a 32-bit answer. Once again, this makes sense because I'm multiplying two 16-bit operands. That enables me to store my results into the result2 variable. This is the end of part 1. Make sure you go to part 2 because it deals with signed integer multiplying.